Hello calculus fans, and welcome to section 7.8 where we talk about improper integrals. Up until now we have required definite integrals to satisfy two properties. First, the interval of integration, AB, must be finite. So we had A and B were numbers, they were not infinities, right? So we'd integrate between, say, -1 and 4, but the integrals were finite. And second, this function, this integrand that we're integrating, the function we're integrating must not have an infinite discontinuity. In fact, when we use the fundamental theorem of calculus, it says right away that f of x is a continuous function on the closed interval AB. So we can't have any discontinuities in here. So we can't have any holes or any vertical asymptotes where it goes to infinity or anything like that. Okay, so we're going to change that now. So in this section we consider definite integrals with definite integrals with infinite intervals, and also cases where the function has an infinite discontinuity in AB. In both of these situations, the integral is called an improper integral. So one that you'll probably see and you've definitely heard of is the normal distribution, bell-shaped curve, Gaussian distribution. Well, this is all over the place in statistics. It's just literally everywhere in statistics. And what this is for this normal curve or this bell-shaped curve, this horizontal axis is just a number line. So for data that follow a normal distribution, most of the data, like 99.7% roughly, will be within 3 standard deviations of the mean. And so what happens is this will be a number line, and basically between -3 and 3 you get most of the data. But in theory, this number line goes all the way from -infinity to infinity. And this curve here, this bell-shaped curve, is asymptotic to this line, so it never touches the line. But because we're using probabilities here, we use this to answer questions about probability. So the area under this curve has to be exactly 1. So we have this area under the curve that's exactly 1, and it goes from -infinity to infinity without ever touching it. So basically we have an interval or an integral that looks something like this. We've got this f of x dx from -infinity to infinity. And we know if we integrate this function, and it's sort of a messed up looking function. If you've ever seen it, it's like e to the -x squared over 2 with a whole bunch of other attachments to it. But generally it looks like that. And then when you integrate from -infinity to infinity, you get 1. Well, we're not like equipped to do this kind of integral right now from -infinity to infinity because we need numbers here. So that's what we're going to look at in this section. And this is also used for, well, some of you guys will see this sort of thing if you take differential equations, you run into Laplace transforms, and also determining escape velocity. We need these unusual integrals, these improper integrals. Okay, so let's take a closer look at these. So there's a couple types, basically 2 types. There's the infinite intervals. Okay, this is the first type. And the second type that we'll look at later is the discontinuous integrands, which is a function that has a discontinuity within that interval AB. But first, let's look at infinite intervals. These are improper integrals. I just noticed something, got to make a quick correction here. This should say integrals. So these are improper integrals with infinite integration limits. So they have these forms listed below. So we've got these infinities. We've got an upper limit of infinity, a lower limit of -infinity, or both infinities. So the way that we're going to do this is we're going to use limits. We're going to use limits to do this. So it'll be, well, let's look at this first one, and I'll show you as an example. So this function is continuous on this interval from a to infinity. And the way we're going to get at this is we're going to use a limit. Okay, so it's sort of like this. This is what we're going to do. Let's say, I'll do an example of finding the area. All right, so let's say we're looking for the area under this curve between A and B. Okay, and we're really familiar with doing something like this. So this is y equals f of x. All right, so we're pretty familiar with this interpretation where we think of this as a positive function. We can think of this as the area under this curve between A and B. So what we're going to do now, instead of A and B, let's say we're going to change this B to a T. So this is going to be a T, and we're going to take the limit as T approaches infinity. So it's sort of like this is going to slide along here. So think if we were going to, we're trying to find the area under this curve from A to infinity, so it goes forever, right? So you could think of it like this. What if we found the integral from A to 1,000 of f of x dx? We figured that out. And then we think, okay, what about instead of 1,000, let's go to 1,000,000, and we figure that out. And then instead of 1,000,000, let's go to 1,000,000,000. So we're looking like as we go bigger and bigger and bigger, does this answer converge on a number? So think of it like that. We're looking for the limit. Like as this upper limit gets bigger and bigger and bigger and bigger, does this answer converge on a number, or does it just keep going, getting bigger and bigger and bigger? That's the question. So we have to use limits because remember the fundamental theorem of calculus required these A and B to be numbers, right? Numbers, not infinity. It's got to be a number. So what we're going to do is we're going to answer the question. We're going to think like, if it were infinity, what would we do? Or how would we do it? And the way we'll answer is we're going to take the limit as t gets bigger and bigger and bigger. As it gets bigger and bigger and bigger, and we integrate, does it look like it's approaching some number? So that's the idea. So what that means is we need limits. We need limits here, right? So in this case, we're going from A to infinity. We use a limit. We let t approach infinity. Over here, we're dealing with the other side from negative infinity to b. Well, we can't plug in negative infinity. So we take the limit. We let t approach negative infinity and see if this integral approaches some number. And then if we've got one that's got two infinities here, we can break this up into two pieces. Just like we did in Calc 1 when we had, like if we were integrating a function from 1 to 5, we could go from 1 to 2 and then from 2 to 5. So that's the same sort of idea there. So there's a note here that says that improper integrals are defined as limits. Okay, they're actually defined as limits, so we definitely need limits. Now, I know you guys have been waiting and waiting ever since Calc 1 to do more with limits. Now is your chance. And it's just in this section. We don't really do a lot with limits in Calc 2. But remember, behind everything we do, there are limits, right? Every derivative, every integral is defined as a limit. But here we have to make it very clear that we're using limits, because otherwise we would not be able to do this. Right, the fundamental theorem of calculus doesn't really allow for us to just plug in infinity at an endpoint. So we're going to use limits. We define the integral of f of x over an infinite interval as the limit of integrals over finite intervals. So like I was saying, what we're going to do here to evaluate this, we're going to think of it like this. What if I integrated from 2 to 1,000,000? What would I get? What about 2 to 1,000,000,000, 2 to 1,000,000,000,000? Like, as this upper limit gets bigger and bigger and bigger, does this integral appear to approach a number? That's what we're going to do. So we're just going to use limits to do that. Okay, and we've been using limits ever since Calc 1, so it's not like a new concept. So hopefully this makes pretty good sense. So what we're going to do is we're going to rewrite this. Okay, fundamental theorem of calculus doesn't allow us to just do this and plug in infinity, although that's essentially what it's going to look like. But we want to have a certain level of rigor. This is Calc 2 class, so we don't want to be sloppy. We want to be very precise with our language, right? So I'm just going to rewrite this as a limit. I'm going to say this is equal to the limit as t approaches infinity of this integral from 2 to t dx over x minus 1 squared. So now it's sort of like we're going to treat t just like a number and see what happens as t gets bigger and bigger and bigger. Find the limiting value. So once you get this set up, we can basically just kind of off to the side evaluate this integral, which I'll do over here. So I'll do it over here in red so you can see we're kind of treating it like we've got this integral here, and we've seen these like integrals like this plenty of times. It's kind of a simple u substitution. We let u equals x minus 1, so then du is just going to be dx. So then we really have 1 over u squared du, which of course is equal to u to the negative second du. And from here we can just use the power rule. So to integrate this goes up by 1 to negative 1, and we have to divide by negative 1, right? So we get this like u to the negative 1 over negative 1, which is a really awkward looking expression. I still don't know why the software just has a mind of its own sometimes, but we'll just work with it, right? So this is u to the negative 1. So it's much easier to just write this like this, negative 1 over u, right? This is u to the negative 1. I can bring it down here to make it a positive 1. And dividing by negative 1 is just makes the answer negative. So then we would get this plus c. So this would be the answer to this little one over here. And then we just substitute back in, so we get negative 1 over x minus 1 plus c. So I'm going to take this answer then and put it over in our problem over here. So we're going to have this is equal to the limit as t approaches infinity. And our answer there we got was negative 1 over x minus 1. And now we evaluate from 2 to t. So I'm going to now treat this like a number. I'm going to plug this in. I'm going to act like I'm using the fundamental theorem of calculus here. But then we're just going to take the limit of that result. So I plug in the t. And it's still always a limit until we take the limit. So t approaches infinity. And we're going to have negative 1 over t minus 1. And then we go minus, minus, which makes a plus, 1 over 2 minus 1. Okay, so this gives us a limit as t approaches infinity. Negative 1 over t minus 1 plus 1. At this point, let's take the limit. So now we just have a limit like we had in calculus 1. So as t approaches infinity, I'm going to basically get a denominator of infinity, right? Infinity minus 1, which is still infinity. So I have negative 1 over infinity. So basically we can just make this as close to 0 as we want to, right? Just by letting t get big enough. So we can make this term be as close to 0 as we want, so we can make it not even matter. We can make, this will basically go to 0. And so we're left with the limit of 1, right? Just as 1 remains, this goes to 0, so we get 1. So the answer to this is 1. And I know sometimes it seems a little tedious to write all these limits, but remember, when you are done with college out there making the big bucks, underworked, overpaid, people are going to expect you to be very precise in what you do. They expect you to pay attention to the details. The reason I know this is because I didn't just get out of college and start teaching in college. I was working in some of the jobs you guys are going to have. Worked in manufacturing. I worked in engineering. Worked in an engineering firm before I started teaching. And I can tell you, details are going to matter. So while it would be true that if you just threw infinities in here and didn't use these limits, I would know what you mean. Always think of an example. Let's say you're talking to someone and they say to you, I ain't got none. You know exactly what they mean, but you're probably not going to say, hey, can you do my taxes? Right? You want somebody who's going to pay a little bit more attention to detail, pick up how the English language works. Same thing here. So we're at Calc 2 students, so we can't be sloppy. We want to use our precise language here. So these are limits. So I know. It'd be easier just to throw an infinity up here and not even use a limit, but let's just do it correctly. So we need these limits in here. These are actually limits. Remember, Improper integrals are defined as limits. So we need these limits to be in here until we actually take the limit, and then of course they go away. Okay, enough nagging about limits. Let's see what else we've got here. The improper integrals, like this one and this one, so we got from a to infinity and from negative infinity to a, are called convergent. They're called convergent if their corresponding limits exist. Like the one we just did, the limit exists because we got a number. If it didn't exist, we would get infinity, negative infinity, or in some cases we just get a limit that does not exist. Okay, so when that happens, they are said to be divergent. Usually what that means is the area under the curve is infinite, right? There's some exception, but usually that's what it means. So convergent if the limit exists, meaning we get some number. Divergent if the limit doesn't exist, which means we get infinity, negative infinity, or just some limit that doesn't exist. As an example, if you take the limit as x approaches infinity of the sine of x, well, that limit doesn't exist because if you think of the sine function, as you go out forever, it just oscillates forever. It never approaches any one number. And since it never approaches any one number, this limit just does not exist. Okay. So improper integrals with infinite intervals can be interpreted as areas as long as the function is a positive function, so it sits above the x-axis. This means we can define areas of regions under curves using improper integrals, which is very convenient because we have to be able to do that. So when this function is a positive function and the improper integral diverges, we say the area under the curve is infinite. And we'll see plenty of problems like that. Some of them are actually even a little bit surprising. Okay, but before that, let's just take a look at this one and see what we can do with this example too. Get another improper integral, because this one is going from 1 to infinity. So as soon as we see these infinities here, we're going to need to use limits because it's an improper integral. So this would give us, I'm going to let the upper limit approach infinity. So I'm going to take the limit as t approaches infinity, 1 to t, and then I'm just going to rewrite that integrand 1 over the square root of x is like 1 over x to the 1/2, right? But if I want to use the power rule on this, I'm going to write it as x to the negative 1/2. So let's write this as x to the negative 1/2 dx, because then it's ready to go. We can take the integral right now using the power rule, and this would give us the limit as t approaches infinity of, so x to the 1/2, so we go up by 1, so it makes it x to the positive 1/2. We divide by 1/2, which is like multiplying by 2, x to the positive 1/2 from 1 to t. And I'm just going to rewrite this as 2 times the square root of x from 1 to t. Because we're going to plug things in there, so it's just easier to work with a square root. Okay, so now we're going to go ahead with fundamental theorem of calculus. We're going to plug these in and then take the limit of the result. So we get the limit as t approaches infinity of 2 times the square root of t minus 2 times the square root of 1, which is just 2. And then we take the limit. So in this case, isn't it true that I can make this term as large as I want just by letting t be big enough? So you could make this be more than a billion, more than a trillion, more than whatever you want to just by making this big enough. So basically this goes to infinity. This limit is equal to infinity. And as soon as you see that, we can say that this diverges. So this integral diverges, and we can interpret it because this is a positive integral. On 1 to infinity, this is always above the x-axis. So you can interpret this as being that the area under this curve from 1 to infinity is infinite. It just keeps growing and growing and growing. Okay, so the integral is said to diverge in this case. So for example 3, let's consider the graphs of y equals 1 over x squared and y equals 1 over x. So y equals 1 over x, and we're just going to look in the first quadrant. This one everybody has seen plenty of times. It goes like this, right? It goes through here and then also over here, but we don't care about that. We're just going to look at this. 1 over x squared looks sort of similar here. Of course, it always is, it's over here also, but we just want the first quadrant. So if you look at these graphs, so this is y equals 1 over x squared. This is y equals 1 over x. And what we're going to do is we want to consider this integral 1 over x squared dx. We want to consider it from 1 to infinity. And also over here we want to consider 1 over x dx from 1 to infinity. So we're basically looking at, because these are positive, we can interpret these integrals as the areas under the curve here. And if you look at these curves, this one tends to head towards the horizontal axis faster than this one. But they're similar. Well, it turns out that in this case, with this one, this area is finite. This is a finite area. The area under this curve is a finite area. And when you actually integrate this function, this one converges. This will be a converging integral, whereas this one over here, this diverges. This one diverges, which means that this is a infinite area. Even though they look similar, the expressions are similar, the graphs are similar, not exactly the same, but they're similar. But this one has a finite area where this one has an infinite area. So what happens is both 1 over x and 1 over x squared approach 0 as x approaches infinity. We can see that by looking at the graph. This graph is heading towards 0 in both cases as x gets bigger and bigger and bigger as x approaches infinity. But the difference is 1 over x squared approaches 0 faster than 1 over x, and fast enough to converge. We'll say, and thus converges. It approaches fast enough to converge. Okay, so some of these are a little surprising, and there are some seemingly paradoxical results that come up because of the way some of these integrals behave. You'll see some of these mentioned in the homework problems. We've got a little note here. When we have an integral like this improper integral, we have 1 over x to the p. Well, this is going to converge if p is greater than 1 and diverges if p is less than or equal to 1. And the book establishes this, if you want to take a look in the textbook, in example 4. Example 4 in the book. So if you have the 8th edition, it's on page 530 in the 8th edition. If you're using the 9th edition, it is on page 545 in the 9th edition. And they just go through a little example where it shows this to be the case. All right, so we have investigated the infinite intervals. Now we need to look at the discontinuous integrands. This is the other type of improper integral. All right, so these occur when the integrand has a discontinuity somewhere on the interval of integration. So somewhere between, and as in this case, between -1 and 2, there's some sort of discontinuity here. Okay, so normally what this discontinuity means is the integrand will start approaching infinity at some point. Like maybe the graph has a vertical asymptote or something like that, and that asymptote is within this interval, right, between -1 and 2. So if you look at this one closely, think as you go from -1 to 2, is there anything that could be a problem with this function here? And you can definitely see by looking, well, there's going to be a problem if you plug a 0 in here, right? So this has an infinite discontinuity at x equals 0. Now the thing that can happen here is you might just go ahead and integrate this and not even realize it, and you get some number, everything seems fine, but it's just wrong. It's going to be the wrong answer. So from this point on, we have to be aware that we need to make sure that this function is continuous on this interval. If it's not, then we need to use these techniques of this section for improper integrals. Okay, it hasn't been a problem yet because we haven't known how to do this. So in the homework in Calc 1, when you're learning integrals, the author didn't put one on there like this. Like if we had this, it would have been like from maybe 1 to 2 or something. It wouldn't have been from negative 1 to 2 where we've got this discontinuity at 0. But at this point, from this point forward, we need to always be aware to check and make sure that this function is defined on this interval, and if not, then we need to use these techniques. Okay, so here are the cases. So if you look at this one, we've got this function continuous on open A to closed B and discontinuous at A. So there's a problem at A. So it's something like this. So there's an issue at A. So we can think of it like this. Think of a number line. We've got this number line from A to B, okay? What we're going to do then, we're going to think of the number line like this, open at A, closed at B. So what we're going to do is we're going to approach A but not actually get to A. All right, we're going to approach A from the right. So we're going to take a one-sided limit. We're going to take a limit as T approaches A from the right, from T to B. So we're going to be over here, we're going to approach A but never get there, right? With this limit, we never get to A. We just get infinitely close to A but always bigger than A because we're approaching from the right. Remember from Calc 1 that plus sign means we're approaching from the right? So same thing over here. This time we got a problem at B. So if we've got a number line from, say, A to B, there's a problem at B. So what we're going to do is we're going to approach B from the left but never get there. We'll start at A. So here we're coming in here and we're going to get real close to B but never get to B. Infinitely close but always a little bit smaller than B, right? Because now we're approaching B from the left. So we're coming in from here and we just got a one-sided limit that can take care of that. Okay, the last part is where we have a discontinuity somewhere in the middle, and we're going to do something like you learned in Calc 1, where we'd say something like, it's very similar. If we had this integral from, say, 1 to 10, we could split it up from 1 to 3 and then 3 to 10, right? So we're just going to do that. And then we'll evaluate both of these separately, okay? So when we have to, we'll just split up into two integrals. So let's take a look at this one. So we'll calculate this one using limits by hand, if it exists, if it's not divergent. And then we'll also take a look at how calculators deal with this, because calculators can have a problem with these too. If they don't have computer algebra software, they typically will have a problem with these kind of integrals. So when we look at it, we've got this expression here, and we're evaluating from -8 to 1. From -8 to 1, you can see we're going to go through 0, right? -8 to 1 passes through 0, and you can see there's a problem at 0, right? So let's just make a little note here. There's definitely a problem at 0. A problem comes up at x equals 0. So I'm going to think of it like this. We've got this number line. We're interested in going from -8 to 1, but we know there's a problem at 0. So what we'll do is we're going to approach 0 from the left but not get to 0. Then we're also going to approach 0 from the right but not get to 0. Okay, so we're going to avoid 0, but we're going to get infinitely close to it on each side. So what we'll do in this case, we're going to split this up into two integrals, one on this region and then one on this region. So we're going to say, all right, this is equal to -8 to 0, and then the cube root of x squared, plus, then we'll go over from 0 to 1 of the same integrand. Right, we're going to split it up this way, and now we're going to use limits. I'm also going to rewrite this integrand, so just off to the side here, if you have 1 over the cube root of x squared, all right, isn't that the same as 1 over x squared to the 1/3 power, right? Because the cube root is x to the 1/3 power. That's equal to, remember from algebra class, we multiply these, right? So that's going to be 1 over x to the 2/3, and then that's really x to the negative 2/3. All right, just to get it out of this, because then we can use the power rule here. All right, so what I'm going to do now is put the limits in here. So this first integral is from -8 to 0. So we're approaching 0 from the right, but from the left. Approaching 0 from the left, but we never get there. So what we're going to do here is we're going to say, okay, this is equal to the limit as t approaches 0 from the left, right? So we need that little superscript negative. Remember, we're not writing -0. That's completely different. 0 with the superscript of a negative sign means approaching 0 from the left. Okay, so just so we're clear on that. And then we've got -8 to t, x to the negative 2/3 dx. Then we're going to add this to the limit as t approaches 0 from the right. Now we're approaching 0 from the right because now we're on this little part here. Approaching 0 from the right, the same integrand, so it would be this time from t to 1, x to the negative 2/3 dx. Okay, so now we can integrate this with the power rule. So negative 2/3 goes up by 1, so we have negative 2/3 plus 1, which is like negative 2/3 plus 3/3, which gives us a positive 1/3. Then we divide by 1/3, which is like multiplying by 3. So we end up with a limit as t approaches 0 from the left of 3. X to the 1/3, I'm going to write as a cube root of x from -8 to t. Then plus the limit as t approaches 0 from the right. And again, we're going to have the same answer here, this time though from t to 1. Okay, so at this point we can plug in the endpoints here of our interval. So we get the limit as t approaches 0 from the left. I'm going to plug in the t and I get 3 times the cube root of t minus 3 times the cube root of -8 plus the limit as t approaches 0 from the right, and we get 3 times the cube root of 1 minus 3 times the cube root of t. Okay, so remember we need these details. We're approaching 0 from the left, here we're approaching 0 from the right. So I can now plug in 0. And we have to be careful because sometimes students are so used to have limits at infinity, they plug infinity in here and they say it diverges. It's 0, right? We're plugging in a 0. So to evaluate these limits, remember from Calc 1, we can actually just plug in a 0. Right? To do the limit, we plug in a 0 and we're going to get, this thing will be 0. Now over here, the cube root of -8. So think of, is there a number I can take 3 of, multiply them together and get -8? The answer, of course, is -2. Okay, so this limit is 0. We're going to have the same thing over here. This is also going to be 0. So we basically are going to get -3 times -2, right, which is this right here, -3 times -2, and then plus, over here we get the cube root of 1, which is 1, multiplied by 3, so we get 3. -3 times -2 is 6 plus 3, which gives us an answer of 9. Okay, so if you ask a calculator to evaluate this integral, if your calculator has a computer algebra software system on it, So if you have the TI Inspire, some of the TI Inspires will say somewhere on the front of the calculator will say have CAS. That means it has computer algebra software. Others don't, so they don't all have it. But if any calculator that has this, like I think the TI Voyager 200 or the TI 89, and there's other, Hewlett-Packard, Casio make calculators also that do this. They'll actually get the answer just fine. They'll just say 9. But if you ask the TI 83 or 84, and they just use the Cordic algorithm, they don't have computer algebra software. So if you ask those calculators, if you punch this in, if you go math, right? If you're TI 83 or 84 and press the math button, and then go to 9 for your finite integral command. Well, if you punch this in there, what it will do is it will take a long time. It's going to plug away, and then it's going to give you, I believe it gets close, but it gives you the wrong answer. It's like a weird looking answer. It'll say like 8.999567, just like some number close to 9, but it's wrong. The answer is exactly 9. Sometimes TI 83s and 84s will give like a division by 0 with this kind of integral, or it'll time it. It gives some sort of error, but it doesn't really know how to handle these. Okay, so just keep that in mind. These can confuse software also. But as long as we use limits, we're going to be just fine. We're going to get a number if it converges. If it doesn't converge, we'll typically get some sort of infinity. Right, so let's take a look at one more. And we can see this one is going to be a problem because we're integrating from 0 to 3, and we can see there's going to be a problem at 2. So this one will also give TI 83 or 84 some problems. I think it tells something like it gives you some sort of error if you attempt this on the TI 83 or 84, and it takes a while to get there. But we can see there's definitely a problem with 2. There's a problem at 2. So if you've got a number line here, we go from 0 to 3. Well, there's definitely going to be an issue at 2. So what we're going to have to do is same as always. We're going to approach 2 from both sides. We'll split this up into 2 integrals. We'll approach 2 from both sides, but we won't actually get to 2. So first thing, let's just split this up into pieces. We're going to go from 0 to 2 dx over x minus 2 plus 2 to 3 dx over x minus 2. Okay, and so to get at these, we're going to use the limits, right? We're going to let this 2 become t. We'll let those be t, and we'll take the limit. So we're going to say this is the limit as t approaches 2. Okay, now this one's going from 0 to 2. So from 0 to 2, I'm approaching 2 from the left, right? From values less than 2, I never get to 2. So I need to put a minus sign here. Approaching 2 from the left. And I'm just going to rewrite this as 1 over x minus 2 dx. And this will go from 0 to t. Then plus the limit. T approaches 2 from the right. And so we'll have t to 3, 1 over x minus 2 dx. I'm just writing it like this so it's a little easier to see. And after section 7.4, you should know exactly what this integral is, right? And we've seen a million of these in 7.4. It's a natural log, right? But we have to deal with the limits here. So this from 2 to 3, we're approaching 2 from the right, from values bigger than 2, and we never get there. So to integrate these, again, like I had mentioned, we saw a million of these. Well, maybe not a million, but we saw a lot of them in 7.4. This is an easy U substitution, so if you've done the 7.4 homework, you already know what the answer is. It's going to be the natural log of the absolute value of x minus 2. If you're not convinced, just do a U substitution. And you'll see that you're going to get 1 over U du, which is natural log absolute value of U plus C, which ends up being natural log of x minus 2 absolute value plus C. Okay, so for these over here, we're going to go equals the limit as t approaches 2 from the left. natural log x minus 2. Whoops, and then we have to go from 0 to t, plus the limit as t approaches 2 from the right of the natural log of x minus 2 absolute value from t to 3. So if we plug in these limits now, we will get equals the limit as t approaches 2 from the left of the natural log of t minus 2 minus the natural log. So I'm going to get, I take the 0, plug it in here, I get the absolute value of 0 minus 2, the absolute value of negative 2, right? 0 minus 2 is negative 2. And the absolute value of negative 2 is just 2. So this is the natural log of 2. Plus the limit as t approaches 2 from the right of the natural log of 1, right? Because I plug in the 3, get 3 minus 2, which is 1. Then minus the natural log of t minus 2. And then when you come over here, we can see, okay, we're going to have to draw something here just to make sure. So I'm going to approach 2 from the left, and so I've got this natural log function. So let's just practice the natural log function again. So all logarithms sort of act in a similar way. They all do this. They all go through at 1, right? Regardless of the base, the natural log of 1 is 0. The log of 1 is 0. Right? Let's just practice. A log of any base, it's always 0. Because remember what it's saying? It's saying, let's do this one. So natural log really is base e, right? So what this question is asking is, with this base, what power do I raise that base to turn it into 1? Well, e to the 0 is 1, right? So natural log of 1 is 0. And same thing over here with a common log. If you think of it as base 10, what power do I raise that base to turn it into 1? Got to be 0. Same with log base 7, which you typically would never use, but that's also 0 because 7 to the 0 power is 1. So regardless of the base, natural log or otherwise, they all go through 1. They all do something like this. And then just if the base changes, they get a little steeper. But logarithms, they go to infinity in the slowest possible fashion. Like the person in front of you when you're late to go to Calculus 2, your favorite class. Like that person driving. Sometimes that person drives like the natural log function or like the log function in general. Here's an idea to give you of how slow logarithms are. Let's say this is 1. Let's say we go all the way out here to 5,280. Okay, if you punch in your calculator log 5,280, so go ahead and do that. I'm going to just punch it in real quick. So I'm going to take the log 5,280, and what I get is roughly 3.7. So what that means is if you made a number line and you went out a mile, 5,280 feet, you'd only be up 3.7 feet. You went a whole mile and you raised 3.7 feet. That's how slow logarithms are. So it gets to infinity, but it takes its time. But, okay, we went way overboard on logarithms to make the point that we needed. But anyway, here we go. So the logarithm does this, right? So we've got the natural log of t minus 2, and t is approaching 2 from the left, right? So that means it is getting close to 2 but less than 2, 1.9, 1.99, 1.999, right? Because it's approaching 2 from the left. So there's a number line, here's 0, here's 2. We're coming in from these values below. We're getting really close to 2, but we're not getting there. So when I plug them in here, I'm going to get like 1.999 minus 2, which is a really tiny negative number. So I take the absolute value and I get a really tiny positive number. So basically this argument to the natural log is a really tiny but positive number. So I'm looking at the natural log of like 0.00001, right, and even smaller. So here's the natural log. Here's what y equals natural log of x, and my inputs are really tiny, so I'm getting really small here. Well, as I do that, the natural log is approaching negative infinity, right? So as I get closer and closer and closer here, in other words, the natural log of something really close to 0 but positive, the natural log is going towards negative infinity. So what that means is this limit is negative infinity. So we can just say, at this point we can say equals negative infinity, which means it diverges, okay? And this whole thing diverges. We can stop at that point. And it doesn't matter what happens over here. None of this even matters. If any part of this diverges, the whole thing diverges. So infinities won't cancel. If this is negative infinity and there's a positive infinity somewhere else, we don't add them up. We just, as soon as there's any sort of infinity, you can immediately stop what you're doing and just say this thing diverges. No need to go any further. Okay, so in this case, since this is negative infinity, it diverges, and then we can stop. Okay, so the whole thing diverges. And let's see, what if we didn't notice that asymptote? Okay, let's say we're looking at this problem and we don't even notice. So I've got this problem 0 to 3 dx over x minus 2. And let's say we don't notice it. And we just integrate. And we're like, okay, that's the natural log of x minus 2 from 3 to 0. So we're going to get the natural log of 3 minus 2, which is 1, minus the natural log 0 minus 2, and the absolute value is just 2. And of course, you know the natural log of 1 is 0, right here. Right here's 1, it goes through there. Natural log of 1 is 0, so we would say, okay, this is equal to negative natural log of 2. We get our answer, and you notice there's no red flags, nothing weird happened, and we just get an answer, but it's completely wrong. This is the wrong answer, and the reason it's wrong is because the fundamental theorem of calculus says if f of x is continuous on AB, this is not continuous on AB, so it doesn't apply. All of this is nonsense. None of it works. So with one like this, we just have to be aware that we need to check and see, is this function continuous on this interval? If not, we're going to need to investigate it with limits. Okay? So, as one last little note here, improper integrals must be evaluated in terms of limits, all caps. We need to use those limits. Okay, so that should give you enough to get started. So go ahead and give the homework problems a try. As you know, that's the only way to get better at this. It would be nice if you could just watch me do it and suddenly know how to do calculus. It'd also be nice if we could just watch a few basketball games and then go play in the NBA, right? Make millions of dollars, but it doesn't work that way. Maybe not a good example because I wouldn't be able to play in the NBA even if I practiced. But the point is, we have to get better at calculus. We have to do calculus, okay? So go ahead, open up your book. Don't wait. Try to do the problems and let me know if you have any questions. And I will talk to every one of you very soon.